I will present. And my name is Renata. I'm from Brazil, and I'm assistant professor in the Universidade Federal of de Viçosa. 1 minute, please. I'm an assistant professor in the Federal University of Viçosa, and today I will speak about our last results entitled One Pot Green Synthesis of carbon dots from multi-bagasse waste, characterization and application. This result was done by my student, Luana. Okay. First, I will contextualize the subject of this presentation. Then 140 billion tons of biomass waste is generated annually on the world. Oh, it's difficult. Okay. In Brazil, most of the waste comes from the agriculture sector. Highlights for the brewing industry, because in this process are generating many waste, solid waste, like this bruised spent grains. In this process, bruised spent grains is a solid waste and corresponds to 85% of the total waste generated. For each 10 liters of produced beer, between 1 and 2 kilograms of BSG is generated. BSG is composed of of cellulose and hemicellulose and lignin and ash. Because of its composition, BSG is commonly designated for animal feeding. However, high humidity content causes rapid degradation and contamination. Inadequate management are challenges found in this application. Therefore, it is necessary to develop more novel application of this biomass. Therefore, carbonization to produce carbonaceous materials is an interesting alternative to produce materials with added value. Biomass carbonization can be carried out using biochemical and thermochemical processes. For biochemical processes, specific compounds such as biogas or ethanol are produced, but for thermochemical processes are produced 3 kinds of materials, such as biochar, bio-oil, and biogas. And pyrolysis and hydrothermal carbonization are examples of thermochemical processes. Highlights for hydrothermal carbonization, because this process can be performed under mild conditions of temperatures and autogenous pressure. In the carbonization process, the biomass is added in an autoclave and plus water. This process is called jet pyrolysis because it occurs in the presence of water. The system is stored in a stove by mild conditions of temperature, and many kinds of reactions occurs in the process, such as hydrolysis, dehydration, decarboxylation, polymerization, and aromatization. In this picture, it can be possible to observe the some kinds of reactions. For example, cellulose is hydrolyzed to oligosaccharide, and the cellulose and oligosaccharide is hydrolyzed to glucose, and the glucose is sulfur isomerization, and fructose sulfur dehydration and fragmentation, producing hydroxymethylfurfural and furfural. Other reactions can be occurs in the process, for example, polymerization and condensation, ketoenol tautomerism, intramolecular dehydration, and at the end of the process, it is produced this kind of material, and this kind is a solid. In the process, at the end of the process, is obtained a solid colored hydrogen, and in the same process, by one pot, is generated to a liquid product. In this liquid product is a suspension, and it can be seen in this image. This image is obtained by electronic microscope, and it can be possible to observe spots in this picture that represents the carbon dots presence in this liquid product. It's interesting to say that carbon dots have many surface groups like this, for example, phenol groups, amino groups, and carboxylic groups too. Carbon dots have many properties. For example, they are photoluminescent, they are photostable, and they have low toxicity, and they are very biocompatible, among many other properties. Because of these properties, these materials can be applied in many applications, such as sensors. They can be applied as in the biomedicine. They are used in the photocatalysis. They are used in solar cells, among other applications. Carbon dots are classified into 3 categories. The first one is graphene quantum dots. The graphene quantum dots have a few graphene layers, comprise chemical groups on the edges. And the second one is carbon nanodots. The carbon nanodots have a spherical shape and can have crystalline graphite-like LEDs in carbon quantum dots. And the third one is a polymer dots that have a cross-linkage aggregate linear polymers or polymers chains aggregated around a spherical carbon core. So in this, the object of this work was to optimize the synthesis of graphene quantum dots from Bruce spent grains by hydrothermal carbonization synthesis using Doyle design. For this, we evaluate 2 variables, the temperature of the process and the residence time. To evaluate the characteristic of the best characteristic of the materials, we evaluate the photocatalytic properties. For the experimental design, we evaluate the temperature, and the temperature was studied from 100 degrees to 200 degrees, and the residence time evaluated in this process was from 4 hours to 24 hours. Then we did 9 experiments. These are the conditions evaluating in this design, and it can be is important to say that we did replicates in the central point. To produce the materials, the biomass was added in the autoclave. We used 6.25 grams of the biomass, and we added 50 milliliters of phosphoric acid solution. This solution is important to activate the solid material, and is very important to the reactions that occurs in the process. And the system was stored in a stove by by the temperature and the residence time selected previously. And after the material was centrifugated and for to separate the solid and the suspension. Finally, the material was characterized and applied in the photodegradation of methyl orange dye. In this table, it can be possible to observe the physical-chemical properties of the suspension, and the first parameter evaluated was the pH of the system, and it can be possible to observe that the suspension was very acid. This result is because the use of phosphoric acid solution pot to activate the solid material, and the conductivity was very similar for nine condition of reactions is due to presence of H+ ions presence. About the redox potential, it can be possible to observe that for high temperature produced the small redox potential. This result suggests the formation of more reduced space with increase of the temperature. The zeta potential was evaluated too, and it can be possible to observe that the zeta potential was positive, and these results suggest the presence of positive charges on the graphene quantum dots. About the quantum yield, the result was were similar to obtained in the literature, but highlights for the SA5 and SA7 that used the high temperatures and obtained the bigger results for quantum yield. The suspense was analyzed by infrared spectroscopy, and the characteristic bands was observed in these materials. For example, this band attributed to oxygen-hydrogen bond, and this band is attributed to carbon-hydrogen band, and this band is attributed to carbonyl group, and this band is attributed to carbon-nitrogen bond, attributed to amino groups, and this band is characteristic of a carbon oxygen bond, and this last one is a band characteristic of carbon hydrogen bond. It is interesting to observe that high temperatures produce decrease the intensity of the bands, because the oxygen groups and amino groups are lost with the increase of the temperature. In this picture, it can be possible to observe the UVVs in black color. It can be possible to observe the UVVs absorption, and this first band is attributed to pi-pi antibody transition, attributed to carbon double carbon bond. And this band in 281 nanometers is attributed to N, the transition of N-pi antibody, attributed to carbonyl and amino groups, because of the presence of heteroatoms in the suspension. And in this picture, it can be possible to observe the bright color when the material was illuminated by the UV lights at 365 nanometers. And about the photoluminescence properties, it can be possible to observe a maximum in 327 nanometers. And for emission, it can be possible to observe a maximum at 400 nanometers. The materials were analyzed by electron microscope, and it can be possible to observe graphene sheets. And these materials have the tendency to form agglomerates, and highlights for these graphene sheets that have this aspect. Another characteristic is the presence of hexagonal rings with zigzag edge structures. Then it can be concluded that the suspension have graphene quantum dots in our materials. Then our materials was used in the photodegradation of metyl orange. This is a photo of our system, and the first 20 milliliters of metyl orange was added in a reactor, and plus 20 milliliters of graphene quantum dots, our suspension. It can be possible to observe that we had the control of the temperature, and the system had four UV lamps. Samples were analyzed by UV-Vis spectroscopy at different times of reactions. In this picture, it can be possible to observe the results for each suspension obtained by the experimental design, and it can be possible to observe that the suspension obtained at high temperatures, the photodegradation was very low, below 20% of photodegradation. And for two materials, the suspension obtained at intermediate temperatures, the photodegradation was bigger, 70% of the photodegradation of metyl orange. It is important to say that control experiment that is without graphene quantum dots don't have degradation of the metyl orange. Finally, we have a model, a mathematical model of our data generated by the experimental design, and it can be possible to observe that there is a maximum metyl orange degradation by graphene quantum dots obtained at when the graphene quantum dots were obtained in this range of the temperature. The generated data were adjusted we did a kinetic study of the degradation, and our data was adjusted to pseudo first order mechanism, and it can be possible to observe the presence of two stages of the process. The stage 1, because the stride changed the slope, then the stage 1 was attributed to adsorption of metyl orange on the graphene quantum dot surface, and this is the kinetic constant, and the adjust of the data was bigger, the coefficient of determination was bigger than 0.9. The second stage was attributed to photodegradation, and this is the kinetic constant, and the adjust was very satisfactory with a coefficient of determination bigger, closer to 1. We investigate the process of the degradation, the presence of inhibitors, for example, this without inhibitor, and in the presence of EGTA. EGTA inhibits the vacancies of, because the quantum dots have properties of photocatalyst, and the photocatalyst properties are generated vacancy, electron vacancy pairs, and EGTA inhibits the inhibition of the vacancies, and in this process, it can be possible to observe the one inhibition of about 10%. In the presence of parabenzoquinone, parabenzoquinone inhibits the superoxide radicals, and it can be possible to observe about 80% of inhibition. And in the presence of silver nitrate, the silver nitrate inhibits the electrons auto-generating the process, and it can be possible to observe the about 40% of inhibition. And in the presence of the terbutyl alcohol, this compound inhibit the hydroxyl radicals, and only about 50% of the reaction was inhibition. Then it can be concluded that the superoxide radicals and the electrons photogenerate are the principal species responsible for the methyl orange degradation. Then we propose a mechanism of methyl orange degradation by graphene quantum dots, the UVV lights. This figure represents our graphene quantum dots. These represent the valence band, and this one represents the conduction band. In the presence of lights, the electrons move from valence band to conduction band, and it is interesting to say that surface defects of graphene quantum dots can act as electron scavengers, decreasing the recombination of electron-hole pairs. This occurs because the presence of heteroatoms present in the surface of nanomaterials. The electrons photogenerate to react with oxygen, producing superoxide radicals, and these radicals react with methyl orange degraded this solution. These the equations that represent the mechanism. Then graphene quantum dots are activated by UVV lights, producing electron hole pairs, and in the presence of electrons, that is a mistake in here, because this 2 is subscribed in here. In the presence of electrons, the oxygen produces superoxide radicals, and these superoxide radicals react with methyl orange, degrades this molecule. Then it can be concluded that graphene quantum dots were synthesized from blue spent grains by a sustainable route, and the Doyle matrix design allowed to verify the influence of temperature and the residence time in the graphene quantum dots properties. And the best performance of graphene quantum dots were obtained under mild temperature conditions, and the nanomaterials showed excellent photocatalytic properties. Finally, I wanted to thank my students, the organized committee of the event, the Universidade Federal de Viçosa, the chemistry department, the FIND agency, and thank you everybody for your attention. This is my contact.